So I am Paul Fegan in the Department of Systems Design and Engineering here on campus. It's my pleasure to welcome Professor Epstein to campus. He's a professor of mathematics at the University of Pennsylvania. And a number of years ago, I don't know exactly how many, on the order of 12 or 13, something like that, years ago, your book came out about 10 years ago, is that right? 2? I have the wrong decade. Okay, a few years ago.
It's off by a decade.
Off by a decade.
Seems like 10 years ago.
A number of years ago, we decided to teach a course on sort of medical imaging and looked around for a good standard textbook on the mathematics of medical imaging. Didn't find one, and so ended up producing one. And so that's this Introduction to the Mathematics of Medical Imaging book, which was his. Indeed, I've been corrected. It was from a few years ago. Thank you. And has since then spent a year hanging around with the radiologist and now finds himself giving a talk on mathematical challenges in medical imaging, that kind of workshop. And he'll be speaking to us on inverse problems, an area of particular interest to me, so I look forward to your talk. So I hope that you can join me in welcoming Professor Epstein.
So first, I'd like to thank the organizers for inviting me. And I have to confess that while everybody else we've heard here has been an expert, I'm really an amateur in this field. That I've only worked in it for a few years. And it's been quite astonishing to me how welcoming people in this field have been and how open to this kind of new ideas and new perspectives people are. I've actually kind of made a long path through mathematics before I got here. People were not like that in mathematics. People couldn't wait to see how my ideas could be gotten rid of. So it's quite an unusual experience for me. So my own connection with inverse problems isn't that strong. I started working at, as Paul said, in the radiology department at Penn for Felix Worley a couple of years ago. And the point of that was that I wanted to work in medical imaging, and I was a mathematician, and I know that from past experience that lots of mathematicians who go into medical imaging tend to work on things that could be politely described as completely irrelevant. And I really didn't want to spend my time doing that. In the preparation to writing this book, that he showed, I spent a lot of time reading papers, and very, very few papers written by mathematicians had any real impact in the field. I mean, there were some notable exceptions, like Larry Shep, for example, was a mathematician and a statistician who had an enormous impact in the field. But and I later learned that he spent a lot of time just talking to radiologists, and that's how he found out what the interesting problems really were. And also his natural proclivities force him to work on things that are really interesting problems. But so while I was there, I was just trying to work my way sort of into this subject, and this meant reading a lot of papers and having lots and lots of ideas that I thought were new. And then, of course, you find most of your ideas you'd find in journals. That was something I was familiar with from pure mathematics. And then there's an even worse experience that you have where you find your new idea in somebody's patent. That's somehow much worse than finding it in a journal. But then eventually I did stumble on some problems that had to do with the RF pulse synthesis, which I won't go into any great detail here. It's a sort of a very important part of any MR imaging experiment or NMR spectroscopy experiment. And in some ways, it was a highly developed subject, and in some ways, it was a complete black art. And there were papers in the 90s, late 80s and early 90s, Alberto Grunbaum, and then Peter Morris and Rourke, realized that this was a problem in inverse scattering, a very classical problem in inverse scattering for what's called the 2x2 AKNS system. So I'll just write that down, although I won't spend a whole lot of time working on it. So it's just a very classical equation that was studied very extensively in the early 1970s by Zaharov and Shabbat, first of all in Russia, and then by Ablowitz, Kalp, Newell, and Seger in the US. And this is the inverse scattering problem for this equation is exactly 100% identical to the problem of RF pulse synthesis in NMR. And this is a very fortunate thing in a variety of ways. One reason it's very fortunate is that this is the easiest inverse scattering problem that there is. It has no technical difficulties associated to it at all. And most inverse scattering problems have tremendous technical difficulties associated with it, and you can never really solve them for the kind of data you need, and so on and so on and so forth. This particular problem has none of these issues associated with it. Now, so that's the plus side. The downside is that using these black arcs, the NMR spectroscopists really had found very adequate solutions to pretty much any problem that they were interested in. And so it's very hard to find something really new. We did find things that were different, but it's questionable whether they have any substantive role to play. But I'm hoping someday that they will. I like to think that it's instrumental problems that prevent these more sophisticated pulse synthesis methods from being important. Well, this is something that I've noticed a lot in medical imaging, is that there are lots of inverse problems, and I'll talk about in a minute about what they are. And they're not often formulated as such, or weren't at least initially formulated as such. And the people in the fields found solutions to these problems without ever really formulating as formal inverse problems. And sometimes the solutions were good, sometimes the solutions weren't great. So the early history of the CT scanner is very instructive here. So the first CT, well, somebody told me actually that somebody developed the CT scanner in the 50s. I can't remember who that was, but somebody told me that there was already a predecessor, that Cormack in '63 wasn't really the first person to even build one, that somebody had built one before that. But Cormack built a CT scanner apparently, and he used a lathe as the sort of the apparatus on which he built his CT scanner. And he did not know Radon's work, but he rediscovered the Radon inversion formula, and he rediscovered a whole lot of other inversion formulas that were known for a long time, but nobody had appreciated their significance to this problem. But he kind of was a little unfortunate in that he invented this thing at a time when there weren't sufficient digital computers to do the calculations. You just couldn't really make images. It was just impractical. And so another 10 years passed, and then Hounsfield rediscovered this. And Hounsfield was a true engineer, and he didn't care that there was a Radon transform, and he had never heard of Radon or his transform, or never heard of the back projection formula, and he just thought of it as a linear algebra problem. And he developed what became known as an algebraic reconstruction technique. So he just thought of it as a linear algebra problem with a big matrix. So it was just, you had to solve the matrix equation AX equal to Y, and you figured A out by some, you broke your region up into a grid, and then you put strips through the grid, and you had to figure, so A somehow encoded which blocks the strip goes through. And in the original algorithm, I mean, they had all sorts of problems that we can't even conceive of today. They couldn't even store the matrix A. So what they had to do was they had to compute on the fly the values for the matrix A. So what they did was, it was just too hard to figure out something like the area of the intersection or something. It was just too much of a computation. So what they did was they just decided if the area was bigger than some amount, they put in a 1, and otherwise they put in a 0. And that was how A was computed. And they developed an algorithm that just used the sparseness of A. And as we saw, it gave bad images. And the bad images were for a variety of reasons. And the way that they were working, they could never tell which was which. Because the way they did experiments was that they would put a phantom into the machine and collect the data and then run it through their algorithm. And they didn't simulate the data. They used real measured data. And the problem was that this made it impossible to distinguish algorithmic errors from measurement errors. And Larry Shepp, this was, I think, Larry Shepp's big contribution. He understood, or it just occurred to him, that you could simulate data and then test the algorithms independently of the measurements. So he introduced this notion of what's called a mathematical phantom. And this was a huge advance in the subject, and led to, first of all, the possibility of understanding when you looked at a picture and you saw a certain kind of artifact, what miscalibration of the machine could produce that artifact. And they could then say, oh, well, that's because the detectors are a little bit off-center, that we get that funny little circle over there. And then they could fix the machines up, and so they improved the quality of the machine. They were also able to work on algorithms in and of themselves. And the big advance, I guess, here is probably the RAM-LAC filter, so the RAM-LAC approach to the filtered back projection formula. So that little introduction, maybe I'll I'll talk a little bit more about what are inverse problems. So in medical imaging, we all know what the basic problem is. We want to be able to make images of what's going on inside without going inside. And we don't want to do any damage, or the least damage that we can do. And the way mathematics comes into this is that the measurements we can make are related to the things we're interested in by some kind of mathematical model. So I refer in this lecture to the thing that we want to know about as the system. So we have some unknown system, and we'd like to deduce what that unknown system is. So the basic inverse problem is to determine what the system is from sufficiently many measurements. And this model here in point 2, which relates the state of the system to the measurements, is usually called the forward problem or the forward model. So it tells us if we knew what the system was and we knew what the inputs were, what we would measure as an output. Okay, so very generally, a system would be specified by some collection of variables, which we'll call big X, and the measurements are functions of the variables. And it's kind of a tautology to say that. I'm saying they're functions of the variables. All I'm saying is that the variables actually do describe the system. If the measurements are not functions of the variables, then the variables don't describe the system. So that's a tautology. Now, in most cases, well, in many cases, the map from the state to the measurements is a linear map. And of course, everybody knows that if it's not a linear map, then we have to linearize it, because we're going to be hard-pressed to do anything without linearizing it. So linear algebra is what we can really do in a computer. Okay, so now mathematicians approach these problems, and usually there are 3 steps. And very frequently, mathematicians don't get past the first step. Anybody who's followed the literature in electrical impedance tomography knows what I'm talking about. So the first step is uniqueness. So that is this tautological issue I was discussing a minute ago. Do the measurements really suffice to determine the state of the system? So that's sort of the inverse. Before I was saying that the system is specified by the variables X is just the statement that the measurements are a function of X. Well, here's the inverse question. Do the measurements that we make, are the measurements that we can make sufficient to determine X? So can we go backwards? Are these measurements adequate? So that's the uniqueness question. And then the next question, after you've established, so my friend John Schottland likes to say that that's just a hunting license. First step is to get your hunting license. And that's a step that I think lots of times engineers and physicists don't worry about. They don't worry about that question. Sorry. They often, okay. I did some real damage here. Okay, it didn't work. Could you do that? They take it as obvious. They just take it as obvious that the measurements are adequate to determine X. And then they go ahead and try to find the answer. But mathematicians worry a lot about that question. And in my opinion, I would say too much about that question. Mathematicians like to play the game, actually, of how few measurements can we get away with. On the other hand, engineers all know that the fewer measurements you have, the less likely it is you're going to be able to get a stable result. So mathematicians are kind of working against the grain there, I think. So then the next thing is to find a reconstruction algorithm. So you want to find an exact algorithm that allows you to find the state of the system given that you have exactly measured data, a complete set of exactly measured data. So that's a very idealized situation, but it's a very good place to start. Having an inversion formula is an enormous step up if you're trying to really solve these problems in practice. And once you have that exact inversion formula, and sometimes it isn't a formula, sometimes it's just an algorithm. Sometimes it's an iterative algorithm where, in principle, if you have perfect data and you continually apply this algorithm, eventually you'll converge to the exact correct answer. And then the last step, which is, of course, in many ways the most important for real applications, is to practically implement your reconstruction algorithm in such a way that you get a stable and an accurate approximation to the state of the system. And when I say stable and accurate, I mean that the inverse can be applied to finite, noisy sets of measurements. Okay, here's the simplest example. I like this example because it illustrates what the forward problem is. So here we'd like to measure the height of the mountain, and we'd like to know how far away the center of the base is from us. But there's a big river in there, and we can't go over there. So we can only make these measurements from a great distance. And so what we can measure is the apparent angle from where we're standing up to the top of the mountain. And there's this formula. The tangent of theta is h over L, the height over the distance. And that's the forward problem. That's the forward model. And we can invert that. We see that there are two parameters we'd like to know, h and L. And so it's a pretty safe bet we'll have to make at least two measurements. So we make two measurements, those two angles from two different positions. We also understand that we can measure the distance between the two observation points. And then we can invert the model, and we can get formulas for the answers. So that's a simple case where the model actually is not linear, but we have a forward model, which is very explicit, and we have a forward model, and we have the inverse. And such a formula is useful, as all engineers know, for studying the sensitivity of the output to the measurements in a particular regime. So here, and of course everybody knows that what you want to study are the relative errors. So the relative error in the height divided by is the uncertainty in the height divided by the height. And one just uses calculus when one has a nice formula like that, and you get how a coefficient times d theta 1, which would be the uncertainty in theta 1, the d theta 2 times a coefficient, and then some terms which we presume are small. Although, of course, sometimes they're not small. But for such a formula, you're assuming that those terms are small. And you look here and you see that these coefficients, one or the other, will be very large when theta 1 or theta 2 gets to be close to pi over 2. So that's where you run into trouble. Okay, so here's an example from imaging, a real example. So it's the Radon transform formula. I guess maybe I should apologize, but what's the point? I mean, it's a talk about mathematics of inverse problems. We're going to have to write down lots and lots of formulas, because that's what it's all about, writing down formulas. In the end, of course, if you're going to write a computer program, you have to have a formula. I had an interesting experience, actually, the relationship between formulas and computer programs. So I wrote a first paper in pulse synthesis, and it was filled with formulas for solving these inverse problems. And then I had to write computer programs because I was going to publish it in an MR journal. This meant I actually had to show that it worked. I had to run the algorithm and actually get results. And I discovered in the process of doing that every single formula in the paper was wrong. In some small way, there was a sign wrong here, a 2 there, but every single formula in the paper was wrong. And that was a sobering experience. So here we have the forward model for the measurements in X-ray tomography, which is the Radon transform, which is just the integral of a density function along a straight line. So the straight line is parameterized by S and omega. So just let people know. So omega is a unit vector, and it's the normal to my line, and S is the distance from some fixed origin. So that would be my line, S and omega. Now this is the celebrated Radon inverse formula, which is, well, it looks very simple, but so that thing, H sub S, that's where the kind of the subtlety of this formula hides. That's what's called the Hilbert transform, which it's a complicated thing to think about. It's an easy thing to compute. So that's the important point. This is the nasty part of the formula. I don't know what that S is doing there. That's a mistake. The d by ds is a derivative in this, what's called the affine parameter. And that's what makes Radon inversion a little bit tricky, because it involves taking a derivative, and this is going to be what we'll measure, and it's going to be noisy. And we'll get back to this a little bit later on. And this is what happens when you actually implement that formula. So this is the forward model. The uniqueness theorem follows from the central slice theorem that was presented in Terry's talk, pretty straightforward way. This is the inverse, and that's its implementation as a finite sum. And the tricky thing here is this phi, which captures the tricky parts of this formula, the derivative and the Hilbert transform, in some way that both on the one hand, reflects some qualitative features of that filtering operation, and on the other hand, suppresses the effects of noise so that you get a stable formula. So this Radon inversion formula has some desire to be an unstable formula because it involves taking derivatives of noisy data. So you have to do something to suppress that when you actually implement the formula. Okay, so let me talk a little bit about the structure of inverse problems. So I think of inverse problems as being of sort of two categories. There's this category, the A of x equals y category, where you just have an unknown state and a measurement. And the problem is simply using the measurements to determine the state. So you have some forward model, which is essentially functional evaluation. And lots of, for example, the problem we just looked at, the X-ray tomography inverse problem, fits nicely into that category. It's exactly that sort of a model. The other type of model is a model like this, where x is now an input, which is assumed known, and y is an output, which is assumed known, and b is some additional parameter which specifies exactly which of a collection of possible models I'm actually observing. And the problem in this kind of an inverse problem is to determine b from sufficiently many pairs x and y. Okay, so this is, in principle, these turn out to be somewhat more complicated types of problems to solve than these. And I'll talk about why that is in a minute. Okay, so the first problem, we'll take a linear example of the first problem. So A is just a linear transformation, and we'll just assume here that A is an invertible linear transformation. And we'll assume it's an invertible linear transformation on a finite dimensional space. Now, of course, the problems that we're really interested in, the underlying parameter space is always infinite dimensional. And so these finite dimensional matrices come by approximating an infinite dimensional transformation. And we'll assume that A is invertible, and we'll talk about that a little bit more in a minute. And then we say that the solution is just the inverse operator applied to y. Now, everybody who's done any numerical linear algebra knows that that's the last thing you would ever do. You would never actually compute the inverse transformation unless A were something extremely special like an orthogonal transformation or a unitary transformation. But this is in principle what you do. So you have some numerical scheme that allows you to find x given y. Now, in many problems that arise in medical imaging, A is, at least in principle, invertible. And this really goes to the uniqueness. If A is not invertible, then usually you haven't got the model right, or you need to find a different model because you're not going to be able to determine x from y if A is not invertible. Okay, the problem is that matrices are not all equally good. And there's one number that kind of captures the sort of gross goodness or badness of a matrix, and it's called the condition number. And it's computed in the following way. You take the image of vectors that aren't zero, and you look at the one of, we can just take actually vectors of length 1 instead of not 0, and we look at the one of maximum length, and then we look at the one of minimum length, and we divide those two numbers, and we get a number which is called the condition number. And let me just show what this is. So this is just a little fact about linear transformations. That a linear transformation always maps a sphere to an ellipsoid in any dimension. So in 2 dimensions, it maps a circle to an ellipse. And what we're measuring is the ratio of those two numbers. So this is the transformation A, and the condition number is just the ratio of these two numbers. Now, as I said, A is usually some finite dimensional approximation to an operator in a Hilbert space. And frequently, in problems of interest, this number, the C sub A, grows as the dimension of the space of the approximating space gets to be larger and larger. And for some problems of real interest, it grows very rapidly. Now, what does the condition number tell us? Well, it gives us a relation between the uncertainty in the measurements and the uncertainty in our prediction of what the state of the system was that produced those measurements. And this is, okay, so what this says here is that the relative error, the relative uncertainty in the state, it could be as large as the condition number of A times the uncertainty in our measurements. So we see if the uncertainty in the measurements is large, then the relative uncertainty in our prediction is also very large. Now, why I say it could be as large as, well, this is sort of a worst case scenario. It could also be much smaller than this. But in the case that delta y is not 0 because of noise, then your expectation is that this is roughly the right size. This is the right order of magnitude. So that's what I say. I just use that notation A sort of like B to mean that A could be as large as B. That's not really standard notation, but I needed some notation. Okay, so how do we handle this? Well, the singular value decomposition provides a tool, a very adequate tool, for handling noisy data and getting the most out of your data that's there. And on the other hand, enabling you to control the stability of your results. So the singular value decomposition, and here again, I'll just stick with square matrices so I don't have to worry about multiplying rectangles of different sizes. But let's suppose we have a square matrix. Then we can write it as a product of three terms, where U is a unitary matrix, V is a unitary matrix, and sigma is a diagonal matrix. So unitary just means the rows are of length 1, and they're orthogonal to one another, and so are the columns. And sigma is just this diagonal matrix, so it has sigma 1, sigma 2, sigma n, and then all zeros everywhere else. Now, for those in numerical analysis, I'm not saying that you necessarily can find the singular value decomposition, but let's just say you could. This is what you would do with it. You would, first of all, be able to compute the condition number. So the condition number is just the ratio of the largest singular value to the smallest singular value. So you can tell whether you're in trouble or not by computing the singular value decomposition. Okay, then the next thing you do is you can actually solve the equation, solve the problem, by using this data. So I say that U is a list of columns and V is its list of columns. And I can write, and of course there's something missing there. I can write the solution as follows, that I have to go back. I made a mistake in that slide. I have to go back to the previous slide to see what the right thing would be. Okay, so let me just write the correct thing. So that X is the sum of the inner product between the U's and the data divided by the singular values multiplied by the V's. So here we're just assuming none of the singular values are 0, so we can actually write down the answer. Now we look at that and we see right away that if the sigma i's get to be small, then we're going to be in trouble because we're dividing here by a very small number. Okay, so what do we do in practice? Well, in practice what we'll do is we'll just cut this sum off after a finite number of terms. And there's the cutoff sum at the bottom with the same mistake. The V's are missing, so Vj is missing. But it's the same formula as that, but we've thrown away all of the really small singular values. Now, what we're doing, in effect, is we're trading resolution in the reconstruction for sensitivity to noise. And the reason that is true is that typically, as you go out further and further in the list of singular values, the corresponding singular vector becomes more and more oscillatory. So representing features on smaller and smaller spatial scales. Now, this, of course, is the singular vector if your matrix happened to have as its right factor, the V, the samples of the exponential function along a certain grid. This would be the exact ones. But in most problems, and especially problems that have any kind of a differential equation hidden someplace in the background, what you find is that as you go higher and higher in frequency, in J, so smaller and smaller singular values, correspond to more and more oscillatory singular vectors. And so what you're doing when you're throwing away small singular values is you're just diminishing the resolution. And you can have perfectly, if you actually have the singular value decomposition, then you can just set some criterion where this can be no more than a certain multiple of that as your criterion for where to cut off. Okay, so in principle, this is how one understands the trade-off in a linear problem like this between suppressing noise and obtaining stability and losing resolution. Okay, so here are the other kind of example. And I write it like this. I write it in the form a plus b x is y. So I'm thinking of A as some sort of fixed background model. And the data for my particular problem is all contained in this matrix B. So B is a perturbation of A. And what I'm trying to figure out is what is the perturbation of A. And so what I do is I say, OK, I'm going to put this input xj, and I'll have this output yj, and I'll measure enough of these, and then I'll be able to determine what B is. And so let me just put another step up here. So I have A plus B, and then I have x1, and I put them all next to each other. x1 through xn is y1 through yn. So I call that thing all together some sort of boldface x, and that's some sort of boldface y. And it looks like all I need to do is just invert the x and subtract off the a, and I get the b. And that's what the formula says right there. Just invert the x, and I could just, I'm picking the inputs, so I might as well pick the inputs to be a unitary matrix. So the inversion is cheap and it's stable, certainly isn't going to introduce any problems. Okay, so I could solve for b right there. So it looks like this is an easy problem, and it shouldn't give us any difficulty. Well, but usually the real situation is the following. B is a small perturbation of A. So frequently A is a differential operator and B is multiplication by a smooth function, say. So it's very small compared to A as an operator. So what do I mean it's a small perturbation? Well, one reasonable way to define that would be to say that the norm of B as an operator, as a matrix, is smaller than the smallest singular value of A. So for people who are not familiar with this, the norm of a matrix is just the maximum bx over things with norm equal to 1. So it gives us some idea how much b might potentially stretch something. So we're saying here b is small compared to a. And that's just a reasonable way to say it. Now, okay, if that's the case, it turns out that once again, if b is small compared to a, then the relative uncertainty in our determination of the model is exactly the same as it was before. The situation would be that our inputs will have some uncertainty. There's some noise in our oscillator that produces our plane waves or what have you. And so there's some uncertainty in the outputs, but I'm not even going to worry about that. I'm just going to say all the uncertainty in the outputs is just due to the uncertainty in the inputs. So I'm throwing away a whole source of uncertainty, which is certainly there, the uncertainty due to our measuring apparatus, the noise in our measuring apparatus. I'm just saying the noise in our signal generator produces noise in our outputs. And because A is much larger than B, most of it is just due to the effect of A on the noise. So we got a model like that. And then, once again, we see that the uncertainty in the state, the relative uncertainty in the state of our system is once again determined by the condition number of A and the uncertainty in our inputs. So we see again that in this class of examples, we have exactly the same general phenomenon. That the condition number of the background operator of A specifies the stability of the algorithm. Okay, so conditioning divides matrices into three classes. So we say H is a Hilbert space, and A is an operator on this Hilbert space, infinite dimensional. So A is good if it's invertible. So it's a bounded operator, and it has a bounded inverse. That's what it means to be good. So the Fourier transform is a bounded operator with a bounded inverse. It's a well-conditioned matrix. Bad, or just mildly ill-conditioned, this means that if you look at the singular values of A, they grow faster than, oh, okay, that's really not what I wanted to say. I wanted them to be smaller than. This thing, you can see how I had problems with the formulas in my paper. It's not an isolated incident. So the singular values grow like that, but for some specific m. That they decay at some polynomial rate, but not much worse than that. And then really bad, the ugly, the severely ill-conditioned problems are problems where the singular values decay like that. So, for example, if sigma j behaves something like e to the minus j times m. So those are really bad. So now I want to talk about particular modalities and how we think of them as inverse problems and what kind of conditioning we get. So, of course, everybody's favorite modality, certainly my favorite modality is MRI. And this is the forward model for MRI. Well, this is a somewhat more precise forward model than I had before for CT. So here's my spin density function. And here is my trajectory through k-space. And here is some T2 weighting, so reflecting the fact that the signal actually decays exponentially. And here's some noise process. And that's the sort of initial measurement is this integral plus the noise. And then what I really do, I don't really sample this. So in a lot of literature, we say we're going to sample the function. We never sample anything. That means we never do a functional evaluation at a single point in time. Because if you think about that, that requires being able to generate the delta function. The delta function has infinite energy. You never do that. What you actually do is you average. So you do some kind of averaging. And in MR, maybe the averaging is done very quickly, although, of course, it's a very important part of the measurement process in MR, because this is how you cut off the field of view in the so-called, in the frequency direction. So here psi models the receiver and NJ as a noise process. So the receiver has two nice properties for us in MR. First of all, it helps to diminish the effects of noise, and second of all, and that's extremely important in MR. And if you'd really be in serious trouble in MR if you tried to sample at exact moments in time, because there's a lot of noise, and the noise is white. And what this does, this is a very nice little feature of MR, is that, and sort of it's a nice feature of systems with resonances, is that it allows you to focus your attention on a certain bandwidth around the resonance frequency, and that in effect you're doing is you're band limiting this white noise. So you're taking what is in some sense an infinite energy noise process, and you're filtering it and getting it down to a finite energy noise process, which is what you really need to do. Okay, so, well, the forward model, though, is just the Fourier transform, which is a unitary operator, and you feel like, well, we should be able to do as well as we want with MR, because there is no ill conditioning here. But of course, there's also this term here. There's this exponential decay. And that gives an effective limitation on how far out in k-space we can go. So that's where the limitation in the resolution really comes from. Well, then you could say, well, why don't you just go out faster? You can go out further if you go out faster. But if you go out faster, that means that the support of psi has to be smaller. You have to sample more rapidly. So in effect, what happens is that the noise bandwidth then is increased. So there's these two terms here conspire against you, and they do put something of an effective limitation on how much resolution you can get in an MR image. So here's an image that shows just the effects of noise. So this is the same thing, but this is with 4 signal averages, and this is with 1. And you see that the noise actually degrades the image. No big surprise, but it's just nice to see it. And here is an image that shows the effects of how far out you go in frequency space. So here I think we go out half as far as we go over here, or maybe a quarter of as far. And you can see that there's tremendously more resolution here than there is over there. So those effects are real. Okay, so now X-ray CT. So in X-ray CT, we don't really sample the Radon transform. So according to my principle enunciated before, you never actually evaluate anything at a point. In fact, what we do, well, this is sort of a somewhat simplified model, but it's an okay model, is we average the Radon transform over a collection of lines. So this is, of course, in some ways, this is an archaic model because it's sort of a parallel beam machine, so nobody actually uses these anymore. But it gives the right idea. So instead of measuring the line integral along one line, what we do is we have a collection of lines, and we take some weighted average of the line integrals along all of these lines, and that's what we really measure. Or that's a reasonable model for what we really measure. Now, the Radon the radon transform has this very nice property that this can be understood in terms of the sort of model operator, the radon transform, as being samples of the radon transform of a different function. So it's the original attenuation coefficient smoothed out by essentially what's the inverse radon transform of that function there. So what we're actually measuring is the radon transform of a function which has been smoothed a little bit. Now again, you might feel that this is a bad thing, but in fact this is a good thing, because this function here, this rho, is really not a continuous function at the scales that we're interested in. It's really a discontinuous function. It has a whole bunch of jump discontinuities. And if we really could measure the radon transform of this function, we'd really be in trouble when we tried to use the inversion formula, because it involves integrating functions that are unbounded. And I didn't bring a picture of this, but there's this interesting fact about the radon inversion formula that if your object just is, let's say, a uniform region like that, and you're trying to reconstruct the density inside, you have a certain integral to do, and it turns out to be an integral of bounded functions. So it's actually a very stable calculation. And if you're trying to reconstruct the value of the function outside, which in this case is just 0, it turns out to be an integral of a function of in the interior it's a positive function. In the exterior it's the difference of two integrals, one of a positive function, one of a negative function. Both of the functions in those integrands diverge. So jump discontinuities lead to these kinds of much more difficult reconstruction problems in the exterior region. And you see this in CT images. You see artifacts outside of the head. So that's sort of a nice thing, that the outer artifacts go outside of the head and not inside of the head. But this is a consequence of the radon inversion formula, that there's a difference between the reconstruction problem inside and outside. And even though, of course, we do some smoothing by having a beam of finite width and a detector of finite width, it still is reflected in the lesser stability in the exterior region than in the interior region. And the imaging companies, the manufacturers, have gotten rid of that artifact for good and all, and I don't know how they do it, but when you look at modern images, you don't see it. So it doesn't bother them anymore. Okay, so you need to cut off the data in Fourier space, and as Terry was saying, this is a number I get out of Barrett and Swindell, so I don't know if that's the correct number anymore, but when he wrote that book 20 years or so ago, it was said that the SNR in a CT image is proportional to the 4th power of the radiation dosage. And that gives you some idea why it's very, very hard to improve at a given resolution. It's very hard to improve the resolution in a CT image because you pay a lot in dosage. And as Terry was saying, a lot of people who have these CTs have them frequently. They don't just have one. If you have one in your whole life, it's not that important how large the dosage. But if you have to have one every week or one every 2 weeks, then it becomes a really important question how much you're being exposed to. So just a word, about directions that are sort of growing. X-ray CT as a subject of research for mathematicians was kind of dead for about 20 years. And Larry Shep told me the reason why. I didn't know this. He told me the reason was that because the computations involved in X-ray CT reconstruction were so intensive, they had to be built into hardware. So they had a chip that just did the filtered back projection algorithm, and you could not reprogram the chip. It was just a piece of hardware, and it could only do one thing. Maybe you could fiddle with some parameters, but basically it did one thing. And this made the subject kind of uninteresting as a topic for research, because even if you invented a new algorithm, GE was not going to build a new machine to incorporate your new algorithm. So people kind of lost interest in this as a field for research. But now they've started to build these machines that have many, many rows of detectors, and you can measure 3D data. And there's a lot of interest in how to use that data in the optimal way. So how to write algorithms that will be fast and artifact-free as possible and really use the 3D data. And another interesting problem in X-ray CT, which is still, as far as I know, largely unsolved, has to do with reconstruction from partial data. So let's say what you're interested in is the patient's heart. and you're not interested in anything over there. Well, maybe you could reconstruct the movements of the heart by just using rays that go through a part of the body, just the rays that go through there, let's say over to there, and not over there. So you don't expose the patient to as much radiation. Now, I don't know whether you can do that practically speaking, where you have to turn the tube on and off like that. I don't know if you can actually do it, but let's say you could. That's an interesting question. Can you reconstruct an image from partial data? Now, there's some circumstances in which it's known that you can, at least in principle. So not in this particular instance, but if you're interested in reconstructing what's out here, you can just use rays that lie out here. And this actually was a problem that interested Cormack a lot. And in his Nobel lecture, he talks about this question. So there's a formula that allows you to do this. But the formula is extremely unstable. It's one of these exponentially growing condition numbers as you take more and more terms. So this is a problem that I think people would really be interested to know the answer to. Is there a stable reconstruction formula that works from the exterior in? So again, that's as far as I know, an unsolved problem. Okay, here's just to give you some comparison. This is an X-ray CT image that I got off of the web. Belongs to GE. Soft tissue contrast isn't so good, but you can see a lot of veins. So it's a lot of resolution in this image. Okay, so positron emission tomography, in principle, is the same mathematical model as X-ray CT. You're counting events that occur along a line or in a tube, and you'd like to use those coincidence events to reconstruct a distribution of sources. So that's what you do. You inject the patient with some stuff. The stuff is differentially taken up by different parts of, let's say, the brain, and you'd like to understand where the sources are now located. Now, the problem is that in this modality, the problem is that the energy of the decay is a half an MeV. And this means there's not that much that you can put into the patient without starting to harm them. So the number of counts that are available to reconstruct the image is very small, relatively speaking. And so what it means is that the noise tends to be very large. So the noise in both X-ray CT and in PET is what's called Poisson noise. And it's the quality of the data is proportional to the amount of the data. So the more data you have, the better off you are in a very strong way. So the variance is proportional to the intensity in a Poisson process, is equal to the intensity. So in these problems, even though you have a model, which is this nice, smooth differential model that has a beautiful inversion formula, which is implemented in countless different ways, you can't really use it because the data that you have is too noisy to really plug into the filtered back projection formula, as far as I know. I don't know exactly what is really done. But as I understand it, what is done is that it's something actually a good deal more like what Hounsfield did. They just regard it as a linear algebra problem, and they solve it using methods from linear algebra. Now, there are other ways of doing this. There's what's called a maximum likelihood algorithm. So you say, we have some random process which has these particles, these sources, and we don't know what the source distributions are, and then we have these measurements, and we're going to look for the source distribution such that what we're measuring is as likely as it possibly could be. And this algorithm, I don't know whether that's used in machines, but it's an interesting algorithm mathematically. I think maybe it's a little slow. But in this problem, the point here is that even though you have a good forward model, because the model doesn't accurately enough represent the actual physics of what you measure, you can't use the inverse that it suggests you could use. Or you have to give up a lot of resolution. So you have to do a lot of averaging to get rid of the noise before you can plug it into the inversion operator. Okay, so there's some PET images. And they look really good, but they're really small. And if you blow them up on your computer screen, you find out that there's very little resolution in these images. Okay, so I've grouped these three together, although they don't go exactly together. In principle, they all operate in the same way. They're all what are called inverse scattering problems. And what is an inverse scattering problem? Well, you have some thing in here. And let's say from out here you send in a sound wave. And the sound wave, for example, interacts with this thing. And then you get these sound waves coming out. And then out here somewhere, I measure the scattered field. So I have an incident field and a scattered field. And I have a mapping from the incident field to the scattered field. And I would like to deduce what the object was that did the scattering by measuring enough of these mappings, incident field to scattered field. Now, these problems are very ill-posed. And in ultrasound, ultrasound kind of grew out of sonar. And in sonar, they just didn't bother solving the problem mathematically. They just had ad hoc ways of getting usable results. And that's pretty much what they did in sonar, in ultrasound. They make a lot of measurements. They throw virtually all the data away. They take the data that they know how to interpret pretty well, and they use that data to reconstruct an image using almost no mathematics at all. So they do quite well these days, but they still use a very, very, very simplified model. So for example, they don't model things like the change in the sound speed inside of the body. They just assume that the waves propagate along straight lines, which they don't. But they produce decent images, and images that can be used quantitatively to some extent. But the problem is that, for example, you'd like to be able to average the signal, because you make a lot of measurements in ultrasound, and you'd like to do signal averaging to reduce the noise. But you can't. Let's say you'd like to be able to put the probe in two positions and average the measurements that you get from those two positions, but you can't do them. You can't do that because the model is so inaccurate that there is no real way to compare the data collected over here to the data collected over there. So ultrasound is a modality which could really maybe benefit from some hard mathematical effort. So these inverse scattering problems are severely ill-conditioned. So here's a brief discussion of what inverse scattering is about. So again, you have an incident wave and a scattered wave. And they satisfy an equation something like that. Now, there are lots of different variants on this. So it could be that the k goes in front of the q. And there are lots of, depending upon the physics, there are lots of different variants on this model. This is probably the simplest case. This is just the Schrodinger equation. And what happens is that the wave, the scattered wave, goes out. So this is the so-called Sommerfeld radiation condition. So the scattered wave is diminishing as you go out to infinity in a specific way and oscillating in a specific way. Okay, so in inverse scattering, the measured data are the scattered waves, and you encode the measured data as an operator on a Hilbert space. And we don't have to worry too much about what that means. You can think of it as just a function of two variables, and an incoming variable and an outgoing variable. And the behavior of this as a mapping from a Hilbert space to another Hilbert space depends in most cases nice and continuously on the potential. So I remind you that in this model that I'm thinking about here, my data is in this potential Q. That describes what does the scattering. So, for example, this is the model that's used in the when you're using the Schrodinger equation to study the electron. It's essentially this model. Now, so the data, lambda Q, is the measured data, and it depends continuously on the state of the system. So it's a decent forward model. The mapping from data, from state to data to measured data is good. Now, this is the bad news, though. The mapping from measured data to state, well, it's continuous, but just barely. So you see in the denominator there, I have a logarithm of this quantity that appears over there. Now, I don't expect people to go through and decode that. Let's see what that means. What does that mean? It means if I would like to determine Q of x with 1 decimal place of accuracy, I only need to measure lambda Q with 10 decimal places of accuracy. That's what that's what it really means in simple terms. It means that if you really wanted to use that whole formula there, you'd really be in trouble. You'd have to do extremely, extremely accurate measurements, which you just can't do. Okay, but that's not the end of the story. And the story goes back to the days of microscopy and telescopes, when people were trying to build the best possible microscope and the best possible telescope. And they were interested in doing was improving the resolution. And they kept making better and better and better lenses and more refined designs. And then, sometime in the 19th century, Abbe and Rayleigh analyzed this question, and they realized, using the wave theory of light, analyzed this question. So most of the optical design was done using geometric optics. But using simple application of wave theory, they realized that it actually didn't make any difference at all how you designed your microscope or how you designed your telescope. There was a limitation on the resolution that depended only on the wavelength of the light that you were using to illuminate the object. So this is what is called the diffraction limit. So you have some incoming aperture, outgoing aperture, some stuff in here that's unspecified. You have an object down here. It's being illuminated by light of wavelength lambda. And you look at it up here. And the question is, how much resolution can I possibly get? And what they showed was that the resolution was no better than some multiple of the wavelength of the light. And the exact multiple depends upon things like the length of the object and the size of the pupil and stuff like that. But the real message here is that the resolution was limited by the wavelength of the illuminating light. And people have worked very hard to get beyond the Rayleigh limit, the so-called Rayleigh diffraction limit. And they get a little bit beyond it, but I've never seen anybody claiming that they can get delta x be some multiple of, say, lambda squared. They can get it to be 10, lambda over 10, but they can't get it to be lambda squared. So probably it's a really reasonable expectation that that's it. Now, a similar effect occurs in the wave equation and in many other equations modeled by things like that equation I wrote down before. And it has to do with looking at the free space solution of the Helmholtz equation. And here what I'm doing is I have some solution of that equation, Laplacian plus k squared u is 0. And I look at it here on a plane z equal to 0. And then I let it propagate over to here. And what I'm doing is I'm expressing the solution here in terms of the Fourier components of the solution on the plane z equal to 0. So there's the Fourier transform on the plane z equal to 0, and I get these two terms. The first term corresponds to frequencies less than the wavelength. Lambda here being, well, I think I was using that this was 2 pi, so that lambda is actually 1 over k. So k is the energy, lambda is the wavelength. So I get this term here corresponding to wavelengths, and this should be 1 over lambda squared, and that should be right. Okay, so yeah, there's some mistakes in this formula, but just the usual kind of mistakes. The point here is that the first term corresponds to frequencies, wavelengths less than lambda squared. So this sum squared should be less than 1 over lambda squared. And this is a term that corresponds to wavelengths greater than 1 over lambda squared. And we notice the following thing. The exponential here is purely imaginary. So this is kind of like a Fourier transform. It's a nice unitary operator. It can be inverted. There's no loss of information going from here to here. And it doesn't matter what z is. Z just appears here as a parameter. And it doesn't really change what happens. Of course, there's some decay as z gets larger just because this becomes more and more oscillatory as z gets larger. Now, here, by contradistinction, I have e to the minus 2 pi z over lambda. So z is a positive number. And what that's saying is the wavelengths greater than lambda, the information from wavelengths smaller than lambda is decaying exponentially as I move away from my surface c equal to 0. So this is what is known in physics as evanescent waves. So these are waves that are disappearing exponentially fast as I move away. So this means, in particular, if I move out into the far field where I can measure the scattering matrix, these are gone. These are exponentially lower order than what I can measure. I can't see this at all. That means I couldn't see any information about my object at a wavelength smaller than lambda. That information is just gone. Now, I should say people do beat the Rayleigh limit, and the way they do it is they get really close so that the evanescent waves, there's some of them, are still measurable. So if you make z small enough, this term doesn't get to be too small, and you can get something out of it. Okay, the Born approximation gives another sort of point of view on this. So it's, again, trying to determine q from the scattered wave. So what I do here is I look at my scattered wave out at infinity, and I rescale it by removing the oscillation in the radial direction, and I rescale it by r. So this isn't a measurement you can really do. Of course, out at infinity, the wave is decayed to 0 in amplitude. So you do this at a finite distance. But this is the sort of ideal. And I measure this scattering matrix, which depends upon an incoming direction and an outgoing direction. And if Q is not small compared to the wavelength that I'm using, so it's sort of big, it's a lot of wavelengths, and it's not rough, then I get the following beautiful formula called the Born approximation that says that the scattering operator is nothing but the Fourier transform of the potential at the difference of the incoming and outgoing directions scaled by the energy of the illuminating wave, or 1 over the wavelength. So this formula says you'll have no trouble at all determining the potential in a band-limited sense. So inside of a certain ball in frequency space, the scattering matrix just tells you what it is. And outside of that ball, it doesn't tell you anything. And in fact, of course, there are nonlinear corrections to this formula, and those nonlinear corrections don't tell you very much else about Q outside of this ball in Fourier space. Okay, so I would talk a little. I have 5 minutes?
Yeah.
5. Okay, so in recent work, so I guess the message I'd like to convey here is that these very interesting inverse problems that are connected with impedance tomography, and they're connected with making ultrasound, putting ultrasound on a more mathematical footing, and there was one other there on the list. Oh, magnetic encephalography is another example of this type of a problem. All these problems, probably you could make real progress, but you have to recognize that there are certain limitations that are imposed upon you by the physics. And so recently some mathematicians have really started to recognize this and started to work on reconstruction algorithms that take this into account. So Mike Taylor was working on the acoustical inverse scattering problem. So this is a problem where you have just an object and you send in waves and you see what's reflected out to infinity and you try to determine the boundary of the object. So it's like the potential case I wrote there where the potential is infinity in here and 0 out there. So it's a singular limit of the potential case. So in some ways it's a slightly easier problem. And what he has shown is that, at least if you look at the linearization of the problem, then as long as you stay within the Rayleigh limit, there should be a stable algorithm to reconstruct the boundary of the object. More recently, Roman Novikov has given a nonlinear algorithm for determining the potential in the Helmholtz equation or the Schrodinger equation. Again, as long as you stay within the Rayleigh limit. The last thing I want to talk about is diffuse optical tomography. So this is a modality where you send in, let's say, a laser beam there, and let's say this is a breast compressed between 2 plates, and the light makes many, many, many scattering events. And eventually it comes out here, some sort of diffuse arrangement of light. And you measure that, and then you measure lots of these. So you have detector positions and source positions, and you make many of these measurements, and you try to figure out what's happening, what's absorbing the light in here. So what's scattering the light and what's absorbing the light. Now, this modality exists because of the fact that human tissue is fairly transparent to a certain wavelength of infrared light. So this means there's not too much absorption. So you can actually measure something over here. You actually get something coming through. Mostly, we look at our hand, the hand looks pretty solid. But if you illuminate it at the right frequency, there would actually be a lot of light coming through. And this modality seeks to reconstruct either the absorption or the scattering. And this modality has this funny fact about it, that it's entirely ill-conditioned. All of the measurements are exponentially. As you're moving away, as the detector moves away, well, it's sort of as the distance between something like the source and the detectors moves away from either the source or the detectors, you get exponential decay. So you have to, first of all, realize that in order to get anything, you're going to have to make a vast, vast number of measurements, because you're going to have to do a lot of signal averaging to get rid of the noise. And so John Shotland recently has been doing an experiment where he uses for his detector a CCD. So he collects, 10 to the 10th samples. Now, of course, there wouldn't be too much you could do with 10 to the 10th samples in most instances. But he found that in this planar geometry, he could actually work out the SVD, the exact singular value decomposition of the operator that he needs to invert. And so he has an analytic solution. And because he has a formula, he doesn't have to iterate. He just uses it. He goes through it once. He's able to actually compute and he's actually able to solve the inverse problem. And he gets rather good resolution in the transverse direction, and rather poor resolution in that direction where the exponential decay is occurring. So here's some diffuse optical images, and you can see. So here it's this picture that I drew here, where you have the source on one side, the detector on the other side, and you see that the things that are too close to the source and the things that are, this is the distance from the source. The things that are too close to the source and the things that are too far from the source kind of disappear, but the things in the middle plane are easier, are more and more and more apparent and better resolved. So this is an example where, by using special geometry and enormous oversampling, you're able to actually beat the Rayleigh limit. And actually, the resolution in the transverse plane is better than the Rayleigh limit. It's like the Rayleigh limit over 10. So he really beats the Rayleigh limit here. Okay, so just some prospects. So I think that this is mostly for mathematicians, and I might be the only, one of the very few mathematicians in the room. But mathematicians, when working on these problems, have to keep in mind that these are real problems, and these aren't mathematical problems, and that there's a lot of noise. And this is something that's kind of absent from mathematics, both in practice and sort of emotionally. Mathematicians don't like to admit the existence of noise, and they never think about it when they're doing calculations. They like to write complete asymptotic expansions with all terms, and they don't realize that in any real system you can maybe measure the first term if you're lucky, and that all the other terms are kind of just there for fun because you're never going to see them. So there are lots of interesting problems, but mathematicians have to come to grips with the fact that there's a lot of noise in the real world. And I think they should direct their efforts towards problems that will lead to really interesting imaging modalities and not just sort of abstract questions of mathematics. And it also may be the case that it's good to just change the rules of the game. That is, to work on to find new imaging modalities. And this is something that I think it sort of happens in MRI all the time. People are all the time coming up with new physical phenomena connected to magnetic resonance that allow you to find different new contrasts, new ways of forming signals, and it's led to diffusion tensor imaging, and it's led to magnetization transfer imaging. It's led to a whole bunch of methodologies for seeing things that are below the resolution limit of the method, the fundamental resolution limit, but you can still see that they're there. You can't resolve exactly where they are, but you can still see that they're there. So I think that is really probably the best hope for the future, is that mathematicians, physicists, engineers, physicians, they should work together to find new niches in which to do imaging. So that's what I'd like to say.